Section 4.4. It's called the Fundamental Theorem of Calculus. Anytime somebody puts the word fundamental in something with math, it means it's really important. Okay, that's really what it means. It means it's really important. And it is really important. We actually saw pieces of this along the way in 4.1 through 4.3. So let me just kind of remind you of where we've come and why we're here where we are. So in section 4.1, you guys learned to do antiderivatives, and you just took a quiz on them, right? So you're doing this derivative process backwards, essentially, yeah, the opposite of derivatives. And in 4.2, we talked about kind of what that means in terms of areas under curves. So as long as the equation itself is, at least an application of it is, the equation itself is inside sort of above the x-axis, we can take a look at the area that is created when we take our curve down to the x-axis. And we made it with rectangles, right? And then in 4.3, one of the things that we talked about is this idea that there's a connection between the two, between this idea of antiderivatives and this idea of finding these areas with rectangles. And then if we let these rectangles get infinitely narrow, or let there be infinitely many rectangles is another way of saying that we can approximate within whatever level of accuracy we're able to, like perfectly, if you will, using other methods. And in fact, we even talked about how we could do that with some limit ideas and separation of antiderivatives, and we even had the symbols used, but we didn't actually go forth and do that process yet, and that's what this lesson is. So if you take a look at Theorem 4.5, first thing on the page, this is the fundamental theorem of calculus. Now, you'll notice that the first part looks like something we've already talked about. We've already looked at that notation. This is the area under the curve between x is a and x is b, and we're doing the antiderivative somehow, and this new part is actually the part on the right. It tells you what you really do is you take the antiderivative, just like you did on your gateway, and you evaluate. In particular, you evaluate at the top limit value first, whatever's in the top, and then you evaluate at the bottom limit value, and then you subtract. Okay? So it's just like one step beyond what we've done already. We're taking antiderivatives and we're doing some sort of an evaluation process with them. So we're going to do a whole bunch of examples. And I'm also going to show you a cool calculator trick. So if you have a calculator with you, go ahead and grab that out because you're going to need this as we do this, because I want to show you how you can confirm that you can do this correctly with your calculator. Now, what your calculator doesn't do with antiderivatives, just like it didn't do with derivatives, it doesn't calculate the antiderivative or the derivative, right? It doesn't spit out for you a formula, all right? If you use certain calculators, they do. Any of the calculators that say CAS, that's computer algebra system, they actually calculate antiderivatives. We don't allow those calculators to be used until Calc 4. So even our Calc 3 and Calc 2 students aren't allowed to actually do that. We expect them to be able to do it by hand. Just like you would expect, a second grader to be able to add by hand. We don't give them a calculator that adds very quickly, right? We want to know basic addition facts. So this is the same idea. So we're going to take a look at these. Now you've done a gateway, so you know some of these, so this should be really quick and easy. What is the antiderivative of negative 3x? Fabulous, negative 3x squared over 2. What is the antiderivative of the plus 4 part? Plus 4x, fantastic. Now, notation, this is new, haven't shown you this. You're going to draw a bar here on the left, on the right. And whatever the higher number, not higher, but the upper number, doesn't necessarily mean it's bigger, but the upper number is in the limits, gets transposed over there, so that's 5. And whatever the lower value is for the lower limit number, the 2, gets put down here. So that's the notation. Now, this bar at the end is an evaluation bar. We use it in a couple of different places in mathematics, but this is definitely one of them where it's very nice to use it. And you can kind of just see where it's moving from the front to the back of the problem. What does it actually mean? Well, it actually means to take the 5 and to plug it in. So we're going to have negative 3 times 5 squared over 2 plus 4 times 5. And we're going to find out what that is here in just a moment. And then we're going to subtract, and we're going to do the same thing with the 2. We're going to plug the 2 in. So negative 3 times 2 squared over 2 plus 4 times 2.
Why do you not need plus C?
It's a very good question. Can I show you why? Okay, so did you guys hear Jeffrey's question? Where'd the plus C go? And that's a really good question. I really hope you did remember it on your gateway. If you didn't, it's not the end of the world, I promise. So let me show you what happens if we put the plus C in. Do you see it? Yeah, it cancels out. That's why we don't need it. If you put it in there and you want to see it there, that's great. But it's really just not necessary. It will cancel itself out. Cool? Yeah. All right, so I'll leave it there just so that because I don't need to take it out necessarily at this point, but they cancel. All right, so grab your calculator. One of the ways to do this in your calculator is to put the antiderivative you found into y1, negative 3x squared over 2 plus 4x, right? And then you can do, so if we put in to y1 our antiderivative, the capital F that we just found, and then back in the regular screen, you can tell it y1, I didn't mean that, y1 of 5 minus y1 of 2, and you can evaluate. That's one way to use your calculator with this. So go ahead and find out for me what you get for your value on number 1. I'm going to use decimals or fractions actually on this one. Does anybody have an answer? 39 halves. Okay, so negative 39 halves, or if you did it in fraction form, it would be negative 19.5. What would negative mean? I mean, these are supposed to be areas. Any ideas about why this is negative? Oh, we haven't talked about this, so I'm just asking you to speculate. It's a good guess. X values are negative. It's not because the X values are negative. In fact, we know our X values are not negative. Our X values go from 2 to 5. Nope. Also a good guess. Nope. That's actually the typical way we do it, is we do typically see the 5 value minus the 2 value. Okay, well, I'm going to show you in terms of a graph what's happening here in a moment, because I want to show you a couple cool things. Huh? Nope, it's not the slope. Also a good guess.
It goes below the x-axis.
Okay, say that really loud, Katie.
It goes below the x-axis.
The graph's actually partially, at least. Is it partially or all the way? I can't even remember.
It's like partially.
Partially, it's underneath the x-axis. So I'll show you what the calculator is doing in terms of calculating. So one of the things that we happened to talk about back in sections 4.2 and 4.3 is that this finds area under the curve as long as we're above the x-axis. The reality is it finds area between the curve and the x-axis, below the x-axis as well. It just calls the area below negative area, and it calls the area above positive area. And if they are a little bit above and a little bit below, it finds what they call net area, where it just balances the two. So it's just the process that the calculator, not the calculator, but the calculus is actually going through to find the area and finding net area. But I want to show you a couple cool tricks. You ready? Okay, so this is done correctly. There's absolutely nothing wrong with what we did. But what happens if we did this, and when we did it, we actually made an error in finding the antiderivative? That would affect our answer at the end, right? I mean, because your calculator is great, but it's only as good as the person who put the values in. And if you made a mistake when you put the values in, it's going to give you a mistake when you get the value out. Agreed? So if you did this, and then you looked at the answer in the book or WebAssign or whatever, and it's giving you the wrong value, you're sort of stuck because you don't know what you did wrong, where the thing you did wrong may have actually been finding the antiderivative. So let me actually show you how you can also confirm, whether you've got WebAssign or not, that you're getting the right value. So what I want you to take is your calculator, and I want you to put the original equation, this line, negative 3x plus 4, and I want you to put it in y1. So just erase y1, what we had before, put negative 3x plus 4 in y1. Okay, I'm going to show you two things your calculator is going to do. The first one I'm going to show you is very similar to the process when we did before, where it was math 8. Do you remember when we did inderiv? And it calculated a derivative for us at a specific point? Well, it can do the same thing for function integration. So that's what we're doing right here, is called integration. So back out in your regular screen, after you've entered this into y1, I want you to select math number 9. And there's two different things that it could show up as. I'll show you what mine looks like, and then I'll show you, I'll bet yours does. Yeah, I'm going to show you what Jeffrey's looks like. So if you have an older operating system on your calculator, what happens when you press math 9 is it pulls up FNINT. Whose calculator looks like that? Okay, Reed, Zach. Okay, so for you guys, here's what you're going to do next. It ought to actually put us in parentheses as well. You're going to tell it y1, comma, x, comma, and then you do the lower limit, that's our 2, and the upper limit 5. Okay, that's what your input looks like. Do you remember how to find those pieces?
Mine says that, but it doesn't look like that.
Okay, that's not what I'm talking about then. If it looks exactly like this, so Zach's is the only one maybe?
Oh, are you saying whenever like you press
When you
9,
press the button, it says that and pulls it up. Yeah. The other option is when you press Math 9, it looks like, sorry, I'm going to borrow yours for just a second. It looks like this. And it puts a little box down here and a little box right here. It has a parenthesis with a box inside it like this. And then a D and a box like this. Okay, something like that. Okay, does everybody else's look like this? Yeah? Okay, does anybody's not look like one of these two? Because it should. It's the only thing I've seen anyway so far. Okay, if yours looks like this secondary notation, you're going to actually fill it in much like it already shows up on your screen, right? Like on the cat problem, you're going to put 2 down here. You're going to put the 5 here. You can put y1 here. You could actually put 3x minus 5 or plus 5, whatever it says. You could do that too. But we've already saved it in y1, and then you can put your x right here. Okay? Whichever version, this one right like my calculator or this one like I pulled from Jeffrey's calculator, when you do that and you press enter, it will give you the right answer. Okay? Because it doesn't actually even calculate an antiderivative. It actually uses numerical methods with those rectangles and does infinitely many rectangles in between. It calculates it numerically. The only thing that might happen that might be a little bit weird is what happened before when we did numerical calculations. So if the answer, for instance, is negative 19.5, and it has so many calculations, it might actually show you something like negative 19.4999999. Do you remember when it's done stuff like that before? And we recognize the calculator's got a little problem with rounding. That's what we recognize, okay? So that's the only thing that could happen that would be sort of maybe a little bit off. But at everybody's calculator, give them negative 19.5 or negative 39 over 2. Yeah? Fabulous. Okay, let's try one more thing. This is so cool. Are you ready? Okay, go back in your calculator where you did y equals, and make sure you put y1 is equal to the negative 3x plus 5, okay? Or 4, whatever it was. Negative 3x plus 4. Okay, so say that in your y equals. Yes? Okay, I'm going to make sure that all your windows match mine. So I would like for you to do your window. Actually, I'll do it to just say, let's just do zoom. I want you to do zoom standard. Is that zoom 6? I think it is. So do zoom 6. Okay, does it look just like a line? Everybody sees a line? Okay, cool. All right, so what you're going to do next, let me get mine to show up so that I've got the same thing going on as you. Oh, my goodness. Got plot on. The effect will be better if I eliminate part of the graph. Let's change your window just a little bit. Make your x minimum 0. Your x maximum can stay at 10. And make your y minimum negative 5 and your y maximum 5. So it just zooms it in a little bit. Let me write those down. So x min will be, what did I say, 0. Your x max can still be 10. That's fine. And then your y min is negative 5, and your y max is 5. It just zoomed it in a little bit because I want to show you some cool. Okay, you ready? Okay. So I want you to hit second trace, which is the calc menu. Okay. You should have some options, like number 1 says value, number 2 says 0, number 3 says minimum. Do you guys see all those kinds of options on there? What does number 7 say? Yeah, it looks like an antiderivative, right? It's got the script s. It says mine says f of x and then dx. Does yours say something like that for option number 7? Okay, select option number 7. On your screen, it should say lower limit, does it? What is our lower limit? 2. Type 2 and press enter. And then it should say upper limit. What does your upper limit say? Or what is our upper limit? 5. So press 5. Or hit 5 and press enter. And then press enter. And what did you see happen? I didn't give a good very graph. It shaded it in, didn't it? I still didn't pick a very good window. If we, let's make my window go down to y minimum of negative 10, it would have been better. So if you change it to y minimum 10, I think it would have been better. go through the process again. Number 7. Lower limit 2, upper limit 5. And it shades. Okay, did everybody shade it in? Some of you have really cool calculators that shade it in color. Mine's grayscale. Boring. Okay, but do you see that the answer is also on the bottom of your screen? All right, so there's a really cool feature, right? I mean, it's got this wonderful visual to it, and that's fantastic. There is a catch to this. Your window absolutely has to include the x minimum and the x maximum values. When I had you set it up, it didn't include the correct y value minimums and maximums, and that will actually be okay. It doesn't hurt it in terms of calculation, but the x min and the x max have to be in the window. For instance, if I had told this window to go from x equals 0 to x equals 4, and then I told it that the lower limit was 2 and the upper limit was 5 outside the window, it would have given me an error when I tried to calculate it. Okay? So I just wanted you to see there's a couple options for verifying your answer. You can use the option number 7 within the graphing window, or you can use the regular screen and you can use Math 9 to verify an answer as well. Cool? Okay. That said, there are times when we're going to expect exact answers that your calculator won't be able to help you provide. And that's going to be example number 2. You ready? Why in the world is example number 2 going to be potentially, at least potentially, answers that our calculator is not going to provide? It doesn't do terms of pi. And a lot of times terms of pi turn into radicals when we're doing trig, right? And our calculator also does not keep things in terms of radicals. So anytime you can get an approximation from your calculator, you can do your process like we're going to do and verify that the approximations match, but you can't simply use your calculator to get the answer. So let's give this a try. What is the antiderivative of 1? X. Good. What is the antiderivative of sine of x?
Negative cosine.
Wonderful. Negative cosine of x. All right. The next thing is to put that vertical line at the back and to transpose the numbers. This is pi and 0. So we're going to substitute pi in. So I have pi minus cosine of pi. And I'm going to subtract off 0 minus the cosine of 0. Is that already good so far? So I expect to see this step that shows you've plugged the values into the right place. I expect to see that on your work, quizzes, exams. Obviously, when you're doing WebAssign, you can, shorthand things a little bit, and nobody's going to be none the wiser, right? But when you're writing this out for it to be proofed and to looked at, that's what I want to see. And then after that, you're welcome to use your calculator as long as it doesn't change the values to take irrational values into things that are not irrational, but they're decimals that you've stopped. And that would be the case on this one, because I do see pi in this problem, right? And pi is irrational, and your calculator will try to give you a decimal approximation. So this pi here, it has to stay pi. But what is the cosine of pi? It's what? It's what? Is it 1? Does that sound right? Really close.
Negative.
It's actually -1 because you're on the other side of the circle. Yeah. So think in terms of unit circle over here. The cosine value is on the negative side, so you've got -1. Good job. So there's a negative already here, and now the answer for cosine of pi is -1. So actually the two negatives are going to end up making this a positive on that one. And then over here, of course, the 0 doesn't matter for this. What's the cosine of 0?
1.
It is 1. So that one's the positive one. So there's a negative involved in the problem right here, right? And then I have a 1 right here. So I got lots of negatives going on in this particular problem. Too many negatives. So that one makes that a positive. That makes that a positive. What is the final answer for this question? Yeah, it's pi plus 2. And you can make sure that you're getting the right decimal approximation with your calculator. So let's just check real quick, all right? Put the original equation into y1, 1 plus sine x. And either using Math 9 or using the second trace button, I'd like for you to figure out what kind of value it is anticipating that you should be getting. And make sure you are putting in pi, not 3.14. Like really put in the pi that's in your calculator. There's no reason not to. And the decimal approximation that my calculator gives, what comes next, 29? Yeah. And of course it continues, right? Is that pi plus 2? Yeah, that's pi plus 2. So I can still verify with a calculator the value. It's just not going to be something that I can sort of get the value and sort of back into quite the same way. Does that make sense? Okay, cool. Let me have you write down the next description thing or whatever, and then we'll stop for today. This is the second fundamental theorem of calculus. Okay, write this one down and then we'll stop for today. The second fundamental theorem of calculus says, if you have a function that's continuous on AB, and the antiderivative, capital F of x, is any number down here, that a is any number up to the variable x of the equation f of t dt, then d dx, the derivative of the antiderivative from a to x of f of t dt is f of x. So just write it down, and then I'll say in words what it's saying. Okay, I promise. Just fill in the details. Once upon a time, email used to be the primary mode of electronic communication. Did you know that? I know you're like, man, that's before I was born. It might have been. It might have been. And you used to occasionally get these chain emails that would come out. This is a lot like the memes that show up on Facebook these days and stuff like this, where they show you these things, they say something like this. Katie, take your age, and then add this number, and then multiply by this, and then subtract that and do this. And what happens? And you end up back with the same age you started with. Have you guys seen stuff like that before? Okay. My grandfather, bless his heart, he's 87. And he was on the forefront of when email was the thing. And he still would have been in his 60s. So he was doing really good. But he got these emails and he was fascinated with them. He was like, that is the coolest thing ever. And I looked at it and I'm like, it's really just basic math. Okay? That's what this is saying for the most part. Basically, this is saying if you take the derivative of the antiderivative, you end up back where you started. That's what it says, right? This says take the derivative of the antiderivative and end up back where you started. Now, there's a little caveat to that. It's not 100% what it's saying, but that is the gist of what's going on, okay? So when we come back next time, I'm going to show you how it's not quite exactly what it's saying, but it is the gist of what's going on. Have a great day. I'll see you guys on Wednesday.